Okay, so let us now move on to the problem of finding local minimum in a one dimension as well as in a two dimension array. So we'll start with one dimension array. So what is the definition of local minimum? Okay, so in a one dimension array, something like this, a local minimum is a value such that it is less than elements both to its left as well as to its right, and an array could have more than one such local minimum. Okay, so for this example array here, 5 is a local minimum because it is less than element both to its left as well as to its right. Similarly, 2 is a local minimum, is less than both element at its left as well as to its right, and 1 is a local minimum. 4 is not a local minimum, it is greater than both its elements to the right and left. Whereas, say for example, 3 is not a local minimum because it is greater than the element to its left. It's less than the element to its right, which is okay, but it's greater than the element to its left. So an element should be less than both its elements to the left as well as to the right. So then only you can say that element is a local minimum. So in an array, there could be several elements that could be a local minimum. Okay. So what we are interested in is to find just one local minimum in an array. Okay. We are not interested in finding all the local minimum values that exist in an array. We just want to find one local minimum in an array. Now, this also kind of is a problem to show you how to prove some properties. Okay, so this is an example again for proof of correctness, and we'll do that quite soon. So what we want to state is this: so if an array satisfies these three conditions, we say it's guaranteed to have at least one local minimum, and we'll soon prove that. But let us see what are the three conditions that the array need to satisfy. So first of all, the array should have at least three elements, and that makes sense because we say by definition an element is local minimum if it is less than the element both elements to its left and right. So there should be at least three elements in the array. Then the first two numbers of the array should be decreasing and the last two numbers of the array should be increasing. So it's like this: the first two or numbers here are 8 and 5, they are decreasing, and the last two numbers should be increasing, like in this case 1 and 9. So 1 and then increases to 9, 8 and then decreases to 5, and so on. So just the first two numbers and the last two numbers. It need not be like unimodal array, just the first two and last two numbers should be like this. Then the numbers should be unique. Okay, so these are unique values. So if an array satisfies these three conditions, we say the array is guaranteed to have a local minimum. Okay. Now we'll see the proof for this quite soon, but before that we'll look at a binary search algorithm to determine such a local minimum for an array that satisfies these three conditions. Okay. So let us take an example and we'll look at a pseudocode for that as we do this. Well, I did not give a pseudocode, but using this example and explanation, you should be able to come up with a pseudocode similar to the other problem. So we'll again maintain the invariant that the local minimum could be anywhere from the left index to right index. So we'll start with the left index as 0 and right index as 7, in this case last index, and find the middle index, which is left index plus right index over 2, which is 0 plus 7 over 2 is 3. So once we reach a middle index, we'll check whether the value at the middle index is less than both its elements to its left as well as to its right. So in this case, at middle index 3 you have 2, and 2 is less than both its left and right values, which are 7 and 3. So we stop right there and declare 2 to be a local minimum at index 3. So that's it. We don't need to go through the rest of the iterations. On the other hand, let us do this example. We have an array just a little bit changed here. So a middle index is 3. At index 3 you have 7, which is greater than both its left and right elements. So 7 is not the local minimum. So now we need to reduce our search space by half. So that means we have to either go use the portion to the left of the middle index as our new search space, or the portion to the right of the middle index as a new search space. So which one we have to go about? Now to decide that, we will compare the so our middle index is 3. So we'll compare the value at middle index minus 1 to the value at middle index plus 1, and the values are 2 and 3. So 2 is less than 3. So that means the local minimum. So you see here, once you find that the value at, in this case, middle index minus 1 is less than the value at middle index plus 1, we have kind of found the minimum of these three elements. Minimum of the element at the middle index, which is 7, and then to the left and right, which are 2 and 3. What is the minimum among these three elements, which is the 2? So that 2 could be a local minimum provided if it is less than the element to its own left. So we already found that it is less than the element to its right, which is our middle index. So it could be the local minimum if it is also less than the element to its left. So that means our local minimum is somewhere in the left search space. So we can then and we are also sure that the local minimum cannot be at the middle index 3, because the element there is greater than both its left and right elements. So, and we decided that the local minimum would be in the left search space. So it's time to move the right index to the left, and up to what we want to move. The middle index is 3, and that value cannot be the local minimum in this problem. So it's clear that if you want to maintain the invariant that the local minimum is somewhere between the left and right index, we have to move the right index to middle index minus 1, because that's now our range where the local minimum is. So we set the right index to be middle index minus 1. So left index is 0, right index is 2. The new middle index is left index plus right index over 2, which is 1. So the value at index 1 is 5. It is less than the value to its left, but greater than the value to its right. So that means 5 is not a local minimum. So now we need to decide whether to move to the left or right, and then reduce the search space. So you see that the element at middle index plus 1, which is 2, is less than the element at middle index minus 1, which is 8. So that means the local minimum will be towards the right, so of the middle index. So that means it's time to move the middle index to middle index plus 1. So it's time to move the left index to middle index plus 1, because the value at middle index cannot be the local minimum. So only we have found that the value to its right could be the local minimum. So we move the left index to the right and set it to be the middle index plus 1. So middle index is 1. So left index is now middle index plus 1, which is 2. Right index is also 2. So the moment again the left index equals right index, because like the previous problem, the invariant property is the local minimum is somewhere between the left index and right index, including the left and right index. So at the moment left index equals right index, that's where the local minimum is. So middle index is also 2, left index plus right index over 2, and at index 2 we can find the element to be less than both its element to its left as well as to its right. So we say it's a local minimum. So again, if the array satisfies these three properties, we don't even need to check at this point. When once the left index equals right index, we can say at the local minimum is at that index. We don't need to compare the element to its left as well as to its right, if the array satisfies these three properties. Okay. Let us do one more example, or before that, any question? It should be easy to understand. Okay, Okay, so let us do the second other example and then the time complexity analysis, and then we'll move on to the proof. So given this array, so again the first two numbers are decreasing. So here we have -2 and -5, so they are decreasing. And then the last two numbers should be increasing, -8 and 10, so that's increasing. The elements are unique and there are at least 3 elements, so it satisfies those 3 conditions. So start with the left index as 0, right index as 10, the middle index is 0 plus 10 over 2, which is 5. So at index 5 we have 7, which is greater than both its left and right elements. So at index 5 you cannot have the local minimum. So how to decide whether to keep the left or right search space? Find the minimum of the two neighbors. So m minus 1 and m plus 1, we find the element at index 6, which is m plus 1, is the smaller of the two neighbors of this middle index. So that means the local minimum is probably in the right search space. So we can move the left index all the way to m plus 1 and keep the right index as it is for this iteration. So left index is 6, right index is 10, middle index is 6 plus 10 over 2, which is 8. So at index 8 we have 0 as the data, and it is less than the value to its left but is greater than the value to its right, which is -8. So 0 is not a local minimum. So which of the two neighbors is a minimum? So -8 is the minimum, so that means the local minimum is to the right. So that means we can move the left index now all the way to middle index plus 1, which is 9. The right index stays at 10, middle index is left index plus right index over 2, which is 9. And then at index 9 we can again compare the element to its left and right. -8 is less than both 0 and 10, and we can stop telling we have found the local minimum. Now we can see there are 3 different examples, each illustrating different possibilities. So the key thing to understand is this: we don't need to go through all the required number of iterations. So the second example is illustrating the maximum number of iterations, and that will happen when that will happen if we have to do the iterations until left index equals to the right index. But we don't need to go through all such iterations. The moment we found at the middle index the value at the middle array value at the middle index is less than the element to its left as plus to the right, we can stop and say we have found the local minimum, and that's what we do in the first example as well as in the third example. So in either of them the left index is not yet equal to the right index, but before then itself we have found a middle index where the value is less than its elements to its right as well as to the left. Okay, so that's the way to interpret this algorithm when it's working. So that means when you write the pseudo code, and I have not shown the pseudo code because I wanted to think about how to write a pseudo code given that we have gone through several algorithms with pseudo code. So we will write a loop and run the loop until left index is less than the right index. But we should be adding the code such that we compare the value of the element at the middle index to both its left and right, and we break from the loop if that element is lower than both its left and right neighbors. Okay, so there should be a break statement somewhere in the loop to break from it and say we have found the local minimum. Right, so any question on the logic of this algorithm for this problem? Okay, so let us now do the time complexity analysis and then we'll move on. Okay, so what we do here, we start the problem of size n, reduce it by half, and how many times we do the basic operation. So the basic operation is again comparison, comparing the element values to its left and right and so on. So think about the number of times we do the basic operation. So to decide which of the two such spaces, whether the left such space or right such space to proceed. So once you find a middle index, we compare it with its right neighbor. So a of m with a of m plus 1, that's one comparison. A of m with a of m minus 1. Now we may be done with these two comparisons if the element at middle index m is the local minimum. We compare it with the element at m plus 1 and the element at m minus 1. If it is less than both of these neighbors, we can say that's the local minimum. But what if the element is greater than at least one of its two neighbors? Then we have to do a third comparison, comparing the elements at middle index minus 1 and middle index plus 1. So basically we want to find which of the two neighbors is the lowest or minimum. So we can then say that could be where the local minimum is and move it to the left or right index accordingly. So we do a total of 3 comparisons at the worst case to decide which of the two subarrays or the search spaces to go about. And again, this is true for n greater than 3. If n is equal less than no, if n is equal to 3, because we cannot find a local minimum if n is less than 3. So if n is less than 3, we just need to if n is equal to 3, we just need to do 2 comparisons. You have 3 elements, just pick the middle element and compare it with its left and right elements and decide whether that's a local minimum. So we just need to do 2 comparisons if we have an array of size 3. For array of size greater than 3, this is the recursion we need to solve. Now again, the f of n is 3, is a constant, so we can write it as state of 1, and using Master theorem we can find it as state of log n. Now again, as I said, the function f of n is a constant time function, state of 1, in this case it's 3. So if that is the case, the final answer for its recurrence is going to be t of n is state of log n. Of course you can use Master theorem and prove that that's what it is, but as a property you can always remember something like this. So if t of n equals t of n over 2, so this part is going to be the same always for binary search. You solve only one sub problem, so it's 1 times t of n over 2 plus the time you spend to decide whether to go with the left search space or right search space. And if that's a constant like 1, 2, 3 or whatever number, it's independent of n, the problem size. So it's a constant. So we can say state of 1. And according to Master theorem, we can then find d to be 0. So a is 1, b raised to d is 2 raised to 0, which is also 1. So it's state of n raised to d log n, n raised to 0 log n, which is n raised to 0 is 1. So it's simply theta of log n. Now there's no space complexity, is state of 1 because we do all such comparisons, evaluations on the input array itself. So we don't need any additional space that goes with input size. Okay. Any questions so far on the time complexity analysis? Alright, so let us do the proof of correctness, which should be straightforward by now. So we need to prove this property that if an array satisfies these 3 conditions, then it is guaranteed to have at least one local minimum. So again, what are the 3 conditions? The array should have at least 3 elements, and the first 2 numbers should be decreasing, the last 2 numbers should be increasing, and the numbers should be unique. So we'll prove this by contradiction. So so what we are going to do is this. So we want to prove if the array satisfies these 3 conditions. So let me write down here separately. So these are the 3 conditions. So what we want to prove is, if an array or given an array that satisfies the three conditions or constraint, whatever you want to call it, constraint, implies the array has a local minimum. Now, so what we will assume is, so we'll try to prove by contradiction. So you should have seen this theorem proving technique in discrete structures course or any other math course. So we'll prove by contradiction that assume the array satisfies these three conditions but does not have a local minimum. So we are assuming that this is the case. So we want to now explore whether this is possible. Given that the array satisfies all these three conditions, is it still possible for it to not have a local minimum? Alright, so let us go about doing that. So one of the conditions is, as you see, the first two numbers should be decreasing. So the first two numbers are decreasing. So let us take the two numbers to be how to do that, at 0 and index 0 and index 1. So the elements at index 0 and index 1, they are decreasing. Okay. So that means, and again the array should have at least three elements, right? So there should be an element at index 2. Now, since the array does not, our assumption is the array does not have a local minimum, the second element, means element at index 2, cannot be something like this. That means the element at index 2 cannot be greater than the element at index 1. Again, remember the elements are unique. So, since the array does not have local minimum according to our assumption, the element at index 2 cannot be greater than the element at index 1. So in order to maintain our assumption to be true or valid, the element at index 2 has to be less than the element at index 1, right? So again, let me repeat it. So all the three conditions are satisfied. So according to the second condition, the first two numbers are decreasing. So the elements at index 1, 0 and 1 are like that. So element at index 0 is less than the element at index 1. All elements are unique. So we need to decide about the element at index 2, whether it be less than the element at index 1 or greater than the element at index 1. So that's what we have to decide. If the element at index 2 is greater than the element at index 1, then the element at index 1 will be a local minimum according to our definition of local minimum. But we want to maintain the assumption that the array does not have a local minimum. So that means the element at index 2 has to be less than the element at index 1. Now you can keep on doing this. So if you want to decide now about the element at index 3, it cannot be again greater than the element at index 2, because if that's the case, then the element at index 2 will be a local minimum. So in order to again maintain our assumption that even though these three conditions are satisfied, the array does not have a local minimum, then the element at index 3 should be less than the element at index 2. So you can keep on going like this until we reach about the last two elements at index, say, n minus 2 and n minus 1. So what can we say about these two elements? So it will also be like this, right? Because if the previous one at index n minus 3 would be something like this, where it's also going to be less than, so that's going to be greater than the element at index n minus 2. So if you want to maintain that property, we have to keep on decreasing like this. But that if that's the case, then it violates our second condition, that the last two numbers are increasing. That means it should be like n minus 1 like this, greater than the element at index n minus 2, because last two numbers are increasing, means that's what it is. As you see, negative 8 and then the 10 increases. So if you want to maintain this property, then we see that the element at index n minus 2 becomes a local minimum, and that's a contradiction to our assumption that even if the three conditions are satisfied, the array does not have a local minimum. So as we can see, if you want to maintain our assumption, then the element at index n minus 1 should be less than the element at index n minus 2. But if you want to do that, it will violate our what is given. What is given is the three conditions are satisfied. What's given, that the array satisfies these three conditions. So if you want to maintain that condition to be satisfied, then the element at index n minus 1 should be greater than the element at index n minus 2. Then the element at index n minus 2 becomes a local minimum, and that violates or that's a contradiction to our assumption that even if the three conditions are satisfied, the array does not have a local minimum. So that's proof by contradiction. So what we have proved is, if the three conditions are satisfied, implies the array has a local minimum. So this is the kind of property we want to prove. So if you want to prove this, we went about doing like this. So assume the three conditions are satisfied, but the array does not have a local minimum. But what we ended up is, if the array does not have a local minimum, it implies the one of the three conditions get violated, right? Because if you want to maintain the property that the array does not have a local minimum, then you have to violate one of the three conditions. So that's what it is. If the array does not have a local minimum, what we proved is one of the three conditions is violated. So this is like, you should have seen what is called as a theorem. If A implies B in discrete structures, we shall see in this. Not of B, so how do I indicate not like this? Not of B implies not A. So like this, if it rains, implies it is cloudy. On the other hand, if it is not cloudy, it won't rain. Okay, so no rain. So what we proved is, not of B array, if the array does not have a local minimum, it implies one of the three conditions is violated. So if not of B implies not of A implies B. So that means not of this, not of this means not of one of the three conditions being violated, means all the three conditions are satisfied. So that's what it is. So all the three conditions are satisfied. Not of this, array does not have a local minimum, so the opposite is array has a local minimum. Okay, so that's what we prove. There's a name for this in discrete structures, so go back and look at that name. Any question? Okay, so if there are no questions, we are out of time, so we'll stop with this. So let me